Let us start with the first problem in flexibility matrix method. In this, they given two span, that is first span is 4 meter and second span is 3 meter. Then first span is loaded with UDL, uniformly distributed load of value 60 kilonewton meter. Second span, that is BC, is loaded with point load at the center. So if I want to solve this using flexibility matrix method, first we have to find the reactions. If it is point load, it is having 3 reaction. Then if it is roller, 1 reaction upward. At C also 1 more roller, therefore 1 reaction. Therefore number of reaction in this continuous beam, that is 5. Number of equilibrium equation, we know 3 equilibrium equation, that is sigma fx is equal to 0, sigma fy is equal to 0, sigma m is equal to 0. Therefore degree of static indeterminacy is equal to number of reaction minus equilibrium condition, that is 2, that is MA comma MB. So obviously MC is equal to 0, MA is unknown, MB is unknown. So to solve this problem continuous beam, we have to make that into two simply supported beam. Then we have to load with free moment. So where we can draw the release structure, where release structure are the two independent simply supported beam, that is AB and BC. I would consider that beam, that is AB, simply supported beam, then one more BC. So this is unknown. Again here, that is coordinate 1 and coordinate 2. So combination of two rotation A, B and C. So first we have to before drawing conjugate beam, we have to find the free moment. For MAB, that is acted by UDL, therefore WL square divided by 8, MBC WL divided by 4, because that is acted by point load, where W value for first beam, that is 60, length is 4 meter divided by 8, second one 100, point load into length is 3 meter divided by 4. If I do that calculation, 60 into 4 divided by 8, WL square divided by 8, 60 into 4, that is 120 kilonewton meter. Then WL by 4, that is 100 into 3 divided by 4, that is 75 kilonewton meter. So for these two values we have to draw the conjugate. While drawing conjugate beam, we have to divide that moment value divided by EI. So let us draw that conjugate beam. First one is UDL, therefore parabola, shape of the bending moment diagram. Then second one is point load, that wo bending moment diagram, triangular shape. So I will draw those two figures. So first one, parabola, load value is 120 divided by EI. Divided by EI. This is A, B. At the same time, one more beam, that is triangular load, value is 75 divided by EI. So now reactions are RA, RB1, RB2, RC, because A, B and C. We know that if you want to find the rotation in the real beam, we have to find the shear force in the conjugate beam. Therefore, we have to find RA, RB1, RB2 and RC. Therefore, RA is equal to RB1 is equal to area of the parabola, that is 2/3 of base length of the beam, that is 4 meter, into height, that is 120 divided by EI, entire value divided by 2. So this is nothing but delta 1. So if I do this calculation, 2 by 3 into 4 into 120 divided by 2, we will get 160 by EI. So for the second beam, RB2 is equal to RC is equal to, that is triangle, area of the triangle, half into base is 3 meter into height is 75 divided by EI, entire value divided by 2, that is 2L is equal to, if I see 2L, that is a combination of this value and this value, that is delta 2L is equal to RB2 plus RC RB1, not RB2, RB1 plus RB2. So in first coordinate we had only RA value, okay, that is R1L, that is nothing but delta 1L is equal to RA, but delta 2L is equal to, it is having two reactions, that is RB1 plus RB2. Therefore, delta 2L is equal to RB1, that is 160 by EI plus RB2, if I simplify this one, 3 into 75 by 2 by 2, 56.25, that is 56.25 divided by EI, we will get 216.25 by EI. So thing is, if I want to find deflection at 1, that is directly RA, only one shear force. But second unknown, that is our second coordinate, is at B. So there are two shear force. So if I want to find delta 2L, that is deflection at 2, we have to find, that is RB1 plus RB2. As we said, deflection is nothing but shear force. So next step, we have to find the flexibility matrix. So here it is two unknowns, therefore flexibility, order of the flexibility matrix is 2 cross 2 matrix. So let us see how to develop flexibility matrix. So flexibility matrix. So development of flexibility matrix. Our flexibility matrix order will be F is equal to F11, F12, F21, F22. To find F11 and F21, we have to apply unit force at coordinate 1. So if I apply the unit force, so let us see how to apply unit force. So if I consider our beam, this is our beam. So first of this will be the first coordinate, then here second first beam and second beam. This is point B, A and C. At B, this is our first coordinate. Our second coordinate having two components, that is one on this beam, one on the other beam. So if I apply the unit force at this point, it is going to that is due to unit force at coordinate 1, bending moment diagram will be, so I will draw that bending moment diagram. It is going to look like this. So if I apply unit force here, there is no effect on this junction, that is going to be 0. So if I see like this, if I apply unit force, that is 1, moment is equal to 1, that is if I apply 1 kilonewton meter, so this is nothing but F11, F21. So if I apply 1 kilonewton, M by EI, that is 1 by EI. So if I want to find the reaction here, first beam and these two beams, F11 is equal to shear force at this point, that is RA. Okay, if I want to find F22, that is shear force RB1, RB2. Okay, so therefore F11 is equal to, as we said at the beginning, if I want to find RA, first I have to find half into base is our length of the first beam, that is 4 meter, into height is 1 by EI into this portion, that is 2/3. So if I simplify this one, 2 get cancels, 4 by 3 into 1 by EI. This is our first term. So at the same time, F21 is equal to, so if I want to find here this value, obviously it will become 0, RB1 plus RB2. If I want to find RB2, that is, first I have to find area, half into base into height into, so we are calculating this one, therefore this distance, that is 1/3, okay, plus RB2 is 0, therefore if I simplify this one, that is 2 ones are 2 by 3 into 1 by EI. So this is the first two terms. We have to find other two terms, F12 and F22. For that we have to apply, here we applied at coordinate 1, we have to apply at 2. Apply unit force. Next step is applying unit force at 2. So same diagram we have to repeat here. There is not much changes, just I will draw that two beams. So this one will become F12 in its force at 1, deflection at 2, that is the term what we done in previous stiffness matrix method. At the same time we have to apply 1 kilo Newton meter here at coordinate 2, that is F22. So if I apply these things, our bending moment diagram will be like this. I am applying 1 kilonewton meter here. At the same time I am applying 1 kilonewton meter on the other beam also. So if I see the reaction, this is RA, RB1, RB2, RB, this is RC, RB1, RB2, and this is RC. So our moment value, if I apply unit load, that is M by EI, that is 1 by EI here, at the same time 1 by EI on this point also. So if I want to find F12, that is here, so just I have to find the reaction here, that is nothing but RA. F12 is equal to, first I will find the area of this figure, half into base is 4 meter, this is 3 meter, therefore half into base into height is 1 by EI. I am calculating reaction here, therefore this portion, that is 1/3. So if I simplify that one, that is 2 by 3 into 1 by EI. So if I want to calculate F22, if I calculate F22, that is RB1 plus RB2. If I want to calculate RB1, first I have to find the area, half into base into height into, I am calculating here, therefore 2/3, this portion is 2/3, plus if I consider this portion, first I have to find the area, half into base is 3 meter into height is again same, 1 by EI into, I am calculating reaction at RB2, therefore this portion is 2 by 3. So if I simplify this one, so 4 by 2 into 2 by 3 plus, so here it is 2 get cancels, 4 by 3 EI, again 3 get cancels, 2 get cancels, so finally we will end up with 7 by 3 EI. So I got F11, F21, F12, F22. If I write that flexibility matrix, so F11 value is, I can take 1 by 3 common outside, 1 by 3 EI common, therefore first term is 4, second term is 2, third term is 2, F12, F22 is 7. I taken 1 by 3 EI common from all the terms. So next thing is flexibility matrix equation. Same as stiffness matrix equation, we have flexibility matrix equation. That equation gives minus delta is equal to F into F matrix, that is flexibility matrix, into reaction matrix. So these all the matrix we already know. So where delta is, we calculated in previous step. So that is delta 1 and delta 2. If I write in matrix form, delta is equal to first term, that is 160 by EI, second term 216.25 divided by EI. What we want is, we want minus value, just I will take EI common, then I will multiply minus. So or else directly I will take EI common, that is 1 by EI into 160 and 216.25. This is our delta matrix, where R matrix is our unknown, that is MA is unknown, that MB is unknown for us. So just I have to substitute all the values. So I will substitute here minus 1 by EI into 160 216.25 is equal to our F matrix we just now calculated, 1 by 3 EI we taken common inside, that is 4 2 and 2 7, 4 2 2 7 into MA and MB. To solve this one, we have to bring this matrix to the other side. That time MA, then one more term MB, this is the matrix, is equal to, if I bring that to the other side, 3 will come to the numerator, EI get cancels, 3 into 4 2 2 7, this will become inverse because we are bringing down inverse, into, if I multiply this term into minus 160 minus 216.25. If I simplify this one, we will get the value of MA and MB, directly. So just I will do the calculation. First we have to insert this matrix as A and B. So shift 4 dim. First matrix A, order is 2 cross 2, terms are 4, 2, 2 and 7. Then our second matrix, shift 4 dim, matrix B, 2 cross 1, so that is shift 4 dim 2, 2 cross 1 matrix. So values are minus 160, minus 216.25. so now I have to multiply with 3, so I will do that on 3 into, so matrix 1, that is A, inverse into matrix 2. So directly we will get the answer. MA is equal to minus 85.93 and MB is equal to minus 68.12. These are the values. Those values are kilonewton meter. Now we have to draw the bending moment diagram for these values. So if I take the beam, so minus value, that is 85.93 at A, at B again anti-clockwise 68.12. so free moments we have to write, that is for first beam we already calculated at the beginning 120, for second beam that is 75. So this is the bending moment diagram for first problem.